Hi, I'm Kedarnath, lecturer in mathematics. I have 15 years experience in teaching, 8 plus years experience in JEE, mains and advanced. So in this video, I'm going to discuss exclusively types of discontinuity and with examples, with suitable examples. So mainly we have two types of discontinuity. The first one is removable discontinuity, and the second one is non-removable discontinuity. So first we will discuss about removable discontinuity. Removable discontinuity. So in this removable discontinuity, limit of the function at given point is exist. Say the given point is a. So limit of the function at given point is exist. And it is finite. And finite. But the function may be defined at a, may not be defined at a. Though it is defined at a, it is not equal to limit of the function. So that's why we are discussing here what a discontinuity of the function. So why we call this kind of discontinuity is removable discontinuity? Because in this kind of discontinuity, it is possible to remove the discontinuity of the function at given point. How we can remove? Just we redefine the function as the limit of the function at given point is same as the value of the function. So we'll redefine the function. How we redefine? The limit of the function at given point is same as the value of the function. After redefining, so that kind of discontinuity will be removed. That discontinuity will be removed. So that's why this type of discontinuity is called what? Removable discontinuity. Again, in this removable type discontinuity, we have two types. We have two types. So the first one is in this removable discontinuity. The first one is missing point type discontinuity. Missing point type discontinuity. And the second one is isolated point type discontinuity. Isolated point type discontinuity. So first we will discuss about missing point type discontinuity. See, if you observe in the name itself, it has what? Missing point. It means the function is not defined at given point. Okay. First, we'll discuss about first one, missing point type. By name, it has what? Missing point. So as it is also one of the removal type discontinuity, so what we have basically limit of the function at a is exist and finite. It is exist and finite. So the second point is the function is not defined at a. F of x is not defined at a. So here, a limit of the function is exist, but function is not defined at a. So just if you observe the diagram of this y is equal to fx, so just I have drawn a graph of y is equal to f of x. So this is the situation at a. So here, if you observe, as x is tending to a, either of the side, these function values are approaching to what? L. So from the graph, we can guarantee that what? Limit of the function at a is L. But if you observe the function, the graph of the function at a has what? A hole. A hole. And the graph is missing at exactly at a. There is no graph of f of x at a. That means the function is not defined at a. The function is not defined at a. So thus, what we can conclude, here the function f of x has what? Missing point type discontinuity at a. Okay, so the graph of a function in the neighborhood of a will be like this if f of x has missing point type discontinuity at a. That means in the neighborhood of in the neighborhood of a, the graph of f of x will be like this. So it has a what? A hole. And there is no graph at exactly a. So that's why this type of discontinuity is called what? Missing point type discontinuity. Because the graph is missed at a because of the function is not defined at a. Okay, so let me discuss some examples, okay, related to this. Suppose example 1. Suppose f of x is equal to x square minus 4 by x minus 2. So this function has missing point type discontinuity at x is equal to 2. So to show that it has a missing point type discontinuity at 2, what we need to show? The limit of the function is exist at 2. Limit of the function at 2 will be exist. But the function is not defined at 2. So clearly, if you observe, basically it is a rational function. Okay. So this function is defined only when denominator is not equal to 0. So x minus 2 not equal to 0 implies that what? X not equal to 2. So that means here f of x is clearly not defined at x is equal to 2. So now I'm going to find limit of the function. We'll have to check whether it is exist or not. So limit extends to 2, f of x. So limit extends to 2. What is f of x? X square minus 4 divided by x minus 2. So if we apply limit directly, what you'll get? 2 square, 4. 4 minus 4, 0. By 2 minus 2, 0. So 0 by 0 form. So we can't apply limit directly. So we have to think alternative method. Here the alternative method is just numerator factorize because of both numerator and denominator are polynomials. Okay, or it is a basically rational function. So x square minus 4 can be written as x minus 2 into x plus 2. Because 4 can be written as 2 square using a square minus b square formula divided by x minus 2. So now we can cancel x minus 2 and x minus 2. So what is the remaining factor there? X plus 2. So apply the limit. What you'll get? 2 plus 2, 4. So here limit of the function at 2 is exist and finite, which is 4 particularly, but the function is not defined at 2. Hence what we can conclude here, f of x has missing point type discontinuity at x is equal to 2. Okay. So the diagram for this will be approximately like this. Anyway, domain not containing 2. So when x not equal to 2, f of x will be written as x square minus 4 by x minus 2 is same as x plus 2, because x square minus 4 can be written as x plus 2 to x minus 2. Anyway, x not equal to 2, so it is not equal to x plus 2. So as x not equal to 2, then x plus 2 not equal to 2 plus 2, 4. That means f of x not equal to 4. So domain not including 2. So range not including 4. So that means the graph of f of x is equal to, now we have to draw graph of f of x is equal to x plus 2, which not including 2 comma 4. Okay, which is not including 2 comma 4. So but f of x is equal to x plus 2 will represents what? A straight line. So just I am going to draw just appropriate graph. So this will be the situation at x is equal to 2. So the graph of the function at x is equal to 2 has what? A hole. So from the graph, what we can conclude? F of x has missing point type discontinuity. Basically, it has removable type discontinuity. In that particular name is missing point type discontinuity, because the graph has a hole at 2, and also there is no graph at x is equal to 2. So that's why this kind of discontinuity is called what? Missing point type discontinuity. So this is about missing point type discontinuity. Next to in removable type discontinuity, what is the second one? Isolated point type discontinuity. Isolated point type discontinuity. So basically it will be coming under removable type discontinuity. Okay, so that means basically it is limit of the function at a is exist. Limit extends to a, f of x is exist. And the second one is the function f of x is defined at x is equal to a. That means f of a is some finite number. And here also limit is exist and finite. But the limit of the function at a is not equal to the value of the function at a. So that means the graph of the function at a will be situated isolated. The graph of the function at x is equal to a, it is situated isolatedly. That's why this type of discontinuity is called isolated type discontinuity, isolated point type discontinuity. Just I'm going to draw a rough diagram. So which shows that the given function has isolated point type discontinuity at x is equal to a. So this is f of a and this is L. So clearly from the graph, limit of the function at a will be what? L. And it is clearly different from f of a, because this point denotes what? L, and whereas this point denotes what? F of a. So if you take either missing point type discontinuity or isolated point type discontinuity, the graph must has what? A hole at x is equal to a, because these two types will come under removable type. So basically in both cases, limit of the function is exist. Then further, f of a is not defined in missing point type discontinuity. But here f of a is defined, but it is different from limit of the function. So if you observe this thick dot denotes what? This point is a comma f of a. So at x is equal to a, the graph is this is a dot. At exactly x is equal to a, what is the graph of f of x? Exactly a dot. And it is situated isolatedly. And this is the remaining part of the graph. Okay. So that's why by name, why it is called isolated point type discontinuity, because at A, the graph is isolatedly situated. So that's why this type of discontinuity is called what? Isolated point type discontinuity. Now, let me discuss one suitable example with example. Suppose f of x is equal to, have taken box function of sin x when x less than 0 and minus fractional part of cos x if x greater than 0, and it will be 10 if x is equal to 0. So clearly here the value of the function at 0 is 10. Now for this function at x is equal to 0, it has isolated point type discontinuity. That means what I have to show here, limit of the function is existent finite and the function is defined at 0, but it is different from the value of the function at 0 is different from limit of the function. And to calculate limit of the function at 0, I need to calculate both left hand limit and right hand limit at 0. So first I'm calculating limit of the left hand limit of the function at 0. So f of 0 minus. So limit x tends to 0 minus. X tends to 0 minus means what? X is approaching to 0 but smaller than 0. That means x value less than 0. Then what you'll get here? Integral part of sin x, or box of sin x. So here x tending to 0 minus means here x is approaching to 0 but less than 0. Like you can take minus 0.1. Minus 0.1 means minus 0.1. It may be either radian or you can take degrees, because when compared to radian, degree measure is some more smaller value. So that point minus 0.1 radian or minus 0.1 degree, it is lies in which quadrant? Fourth quadrant. It is lies between what? Which quadrant? Fourth quadrant. In fourth quadrant, sin x will be what? Negative. That means as x tending to 0 minus, sin x value tending to 0 in that no doubt. Okay, but it is tending to 0 from left side of 0 or right side of 0? It is left side of 0, because here tending to 0 minus means 0 minus is lies in which quadrant? Fourth quadrant. Sin x will be negative and is tending to what? 0. That means sin x also tending to what? 0 minus. So 0 minus means you can take, I told you, example minus 0.1 you can consider. Or if possible, you can take minus 0.0001. So then box of minus 0.1 or minus 0.01 minus 0.001 will be what? Minus 1. So left hand limit will be what? Minus 1. Next I'm calculating right hand limit. So limit x tends to 0 plus minus fractional part of cos x. So basically we have this one. Fractional part of x can be written as x minus box of x or step of x or greatest integer function of x. Okay. Then from this, if you replace x by cos x, what you'll get? Then cos x minus box of cos x. But here we have basically what? Minus fractional part of x. So you take by minus outside of the limit. Then fractional part of cos x can be written as cos x minus box of cos x. So minus, as x tends to 0 plus cos x tending to cos 0, which is 1. minus, as extending to 0 plus. So that means x lies in which quadrant? First quadrant. Then cos x value tending to 1, but it is less than 1 because cos x cannot be greater than 1. Okay, basically cos x tending to 1 means what? Cos x not equal to 1. So now it is tending to 1 means it may be tending to 1 from left side or right side. So here particularly it is not possible cos x will be tending to 1 from right side, because for any real x, cos x cannot be more than 1. So that means here compulsorily it should be tending to 1 from left side. That means here cos x tending to what? 1 minus. So 1 minus means you can consider 0.9, 0.99. So if you take 0.9 or 0.99, etc., for those values of x, box of x value will be what? 0. So that means integral part of 1 minus will be what? 0. Okay. So this value will be 0. So 1 minus 0, what you'll get? Minus 1. So here, left hand limit is minus 1, right hand limit is also minus 1. But the value of the function is 10, which is different from limit of the function. Because your left hand limit is minus 1, right hand limit is minus 1, then what we can conclude? The limit of the function at 0 is exist and finite, and that value is equal to the common value of LHL and RHL, which is minus 1. But it is different from the value of the function at 0. So that's what we can conclude. This function has isolated point type discontinuity at x is equal to 0. Next to what we have, next to one, non-removable type discontinuity. So non-removable type discontinuity, by name it has non-removable, means it is not possible to remove this type of discontinuity. So in this, again, we have 3 different types now. The first one is finite type. Finite type. The second one is infinite type. And the third one is oscillatory type. So the first one, finite type. In this finite type, both left hand limits and right hand limit at given point, say A, they are exist and finite, but they are not equal. So what we can conclude, limit of the function does not exist, because in non-removable basically is what? In any type in non-removable, limit of the function at A does not exist. Already in the starting of the video, I told you this. Okay. So here, what is the reason why here in this case finite type, why limit of the function doesn't exist? Because of left hand limit not equal to right hand limit. But in this case, the difference between positive difference between left hand limit and right hand limit, this will be is the jump of discontinuity. Jump of discontinuity. Jump of discontinuity. The positive difference between left hand limit and right hand limit is called what? Jump of discontinuity. So if f of x has finite type discontinuity at x is equal to a, so in the neighborhood of a, the graph may be approximately like this. Once again, I'm drawing. So the graph will be approximately the situation at A will be approximately like this if f of x has finite type discontinuity at x is equal to A. So here clearly from the graph, what is the left hand limit? L. And what is the right hand limit? M. And here L is not equal to M. Clearly L is not equal to M. So that's why the graph is jumped after A. Okay. After A, the graph is what? Jumped. And how many units it will be jumped? That is the modulus of L minus M units. What is L minus M? The difference between the positive difference between left hand limit and right hand limit at A. Okay. So this is about finite type discontinuity. Okay. Next to infinite type discontinuity. Infinite type discontinuity. So in this type, either LHL or RHL or both are tending to what? Either infinity or minus infinity. Okay. Either left hand limit is tending to infinity or minus infinity, or right hand limit is tending to infinity or minus infinity, or both are tending to either infinity or minus infinity. So in all these cases, what we can conclude, fx has infinite point type discontinuity. Here, infinite point type discontinuity at given point. Okay, infinite point type discontinuity at given point. Here, what I have considered the given point is A. So the graph may be at x is equal to A. The graph may be approximately like this. So here clearly, when x is tending to A plus, f of x is tending to what? L. That means right hand limit of the function at A is L, which is a finite. But as x tending to A minus, so when x is approaching to A from left side, these functional values are what? Increasing indefinitely. So as they are increasing indefinitely, that means that function value is tending to what? Infinite. So here RHL is finite, but LHL is tending to what? Infinite. So LHL not equal to RHL, limit of the function doesn't exist. Hence the function is discontinuous function. But particularly what type it is? Infinite point type discontinuity. So take one more example. So I'm taking an example. F of x is equal to 2 power tan x at x is equal to pi by 2. So this function has infinite point type discontinuity at x is equal to pi by 2. So it is because of as x tending to pi by 2 minus this tan x value tending to plus infinity. Then in that case, f of x tending to what? 2 power infinity. So 2 power infinity is what? Infinity. That means here the left hand limit of the function is what? Infinite. Next, as x tending to pi by 2 plus, tan x is tending to infinity, but it is tending to minus infinity. It is just because of pi by 2 plus means what? More than 90, just more than 90, just more than 90 degrees. Just more than 90 degree means you can consider example 90.1 degree or 91 degree only you consider. So that angle will be lies in which quadrant? Second quadrant. So second quadrant tan x will be what? negative number. So when x is tending to pi by 2 plus, tan x will be tending to infinity, no doubt, but it is plus infinity or minus infinity, minus infinity, because of tan x will be negative when x is tending to pi by 2 plus. Then f of x will be tending to what? 2 power minus infinity. So 2 power minus infinity can be written as 1 by 2 power infinity. But what is 2 power infinity? Infinity. So 1 by infinity what? 0. Okay. So thus here right hand limit of the function at pi by 2 will be what? 0. So here it is a finite. But left hand limit is infinite. So here what we can conclude? F of x is equal to 2 power tan x as in at x is equal to pi by 2. F of x is equal to 2 power, f of x is equal to 2 power tan x at x is equal to pi by 2 has infinite point type discontinuity. Okay. Next, one more example. Suppose if I consider f of x is equal to 1 by x at x is equal to 0. So clearly, when x is tending to 0 minus, 1 by x is tending to infinity, but it is tending to minus infinity because here x is tending to 0 minus, means x is approaching to 0 from left side, means x value negative. Then 1 by x value will be decreasing indefinitely when x is tending to 0 minus. So that means as 1 by x is tending to, as 1 by x is decreasing indefinitely, means what? It is tending to minus infinity. So that means here what you will get? Left hand limit of the function at 0 minus infinity. Then as x tending to 0 plus, then this 1 by x is tending to what? Plus infinity. So that means when x is approaching to 0 from right side, then this 1 by x value will be increasing indefinitely. Hence, what we can conclude, it is tending to plus infinity. So thus RHL of this function at 0 will be what? Plus infinity. So what we can conclude here, f of x has infinite point type discontinuity. Here LHL not equal to RHL, limit of the function does not exist. And particularly here, what kind of discontinuity at 0? Infinite point type discontinuity at 0. So this is about infinite point type discontinuity. And the last one, interesting one, is oscillatory type discontinuity. Oscillatory type discontinuity. Oscillatory point type. Oscillatory point type discontinuity. So in this type of discontinuity, the limit of the function does not exist. What is the reason? Because the limit of the function, it is oscillating between two quantities. Sorry. So the last one, oscillatory type discontinuity. Oscillatory point type discontinuity. So in this type, the limits of the function at given point, it is oscillating between two finite quantities. So that's why the limit of the function doesn't exist. And then automatically the function is discontinuous at given point, and particular name is what it is? Oscillatory point type discontinuity. Because here the limit of the function, the limits of the function at a, means left hand limit as well as right hand limit, both are oscillating between what? Two finite quantities. That's why the name we got here, oscillatory point type discontinuity. So for this, the famous example is f of x is equal to sine of 1 by x at 0. See here, as x tending to 0, then f of x is what? Sine of 1 by x, 1 by tending to 0. So sine of 1 by x is tending to sine of plus or minus infinity. So then this is a oscillatory number, and it is oscillating between minus 1 and plus 1. So as x tends to 0, sine of 1 by x or f of x is what? Sine of tending to sine of plus or minus infinity. But sine of plus or minus infinity is oscillatory number, and it is oscillating between minus 1 and 1. Because you are tending to 1 by x is sine of 1 by x tending to sine of plus or minus infinity means, so that infinity means what? It is a number, a quantity is tending to infinity means what? That quantity is increasing indefinitely. Okay, as x tending to, suppose particularly 0 plus 1 by x tending to what? Infinity. In that case, sine of 1 by x tending to what? Sine of tending to infinity. That infinity, that means here we have to understand 1 by x is a real number. It is increasing indefinitely. As value 1 by x value increasing indefinitely, the sin x value is always oscillating between what? Minus 1 and 1. Minus 1 and 1. Because sin x maximum value is 1, minimum value minus 1. And it is continuous function, so it is oscillated between minus 1 and 1. So the limit of the function does not exist because it is oscillating between minus 1 and 1. Hence, what we can conclude, f of x is equal to sine 1 by x has oscillatory type discontinuity at x is equal to 0. So this is about types of discontinuity. Hope you enjoy the class. Thank you.